Hello class, this is Miss Aya with today's video on sections 12.1 and 2, vectors and components of vectors. As you're watching the video, please remember to write down notes, take down important information, formulas, equations, and examples, and feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what's occurring in the video. At the conclusion of watching the video, write down a brief summary in your notes about what occurred in the video and submit that summary as well as a top question via the online whisk form the day before class. All right, let's begin. And this video will be a little bit longer because we're covering two sections. So let's say I'm at home and I want to go to school, but before I want to go to school, I want to stop at the store. So I go 3 miles due east because the store is 3 miles due east from my home, and then walk 4 miles north of school. And so if I wanted to know how far did I walk, it's easy. I walk 7 miles. But if someone asks, how far is home from school, I wouldn't say 4 miles, 7 miles, just because it took me 7 miles to walk. And I would actually have to come up with the shortest distance between home and school. And I can determine that by drawing a straight line between the two. And we end up with something that is using a right triangle. And then I can use Pythagorean theorem to get that the distance between home and school is 5 miles. Well, that's distance. But today we're going to be talking about something that is used in addition to distance. Distance just measures separation, but the word displacement includes not only the measure of separation, but it also includes the direction, which is something that we haven't seen before in class. So here I have examples of two arrows, and arrows are used to represent displacement. And two components of displacement are not only separation, but also direction. And as you can see, so if we take a look at these two arrows, we can see that they seem to have the same length. The distance from the head to the tail seems to be the same. And here's the head and here's the tail for this one. Seems to be the same length. So they have the same length, but they don't have the same direction. So these two arrows have different displacement. If I go over here and I take a look at this arrow and compare with this arrow, these two arrows have the same direction, but obviously the distance from the head to the tail is different lengths, so they also have different displacements. So all of these arrows here have different displacements, even though a pair may have the same direction, or a pair may have the same separation. So let's take a look at an example. A person leaves her home and walks 5 miles due east and then 3 miles northeast. How far has she walked? How far away from home is she? And what is her net displacement? Well, we cannot answer all these questions because we're missing one important thing. If you notice, it says that she walks 5 miles east and then 3 miles northeast. Well, the question is, what does that look like? And here is here is east, and here's northeast, or here's northeast, or here's northeast. We don't know exactly how far that she walked northeast. We just know the length of the time. And so in order to fully answer this question, we need a picture which gives us, or information that gives us that angle. So here is the angle of the northeast direction that she walked. And we have these lengths. Now we can answer the question, how far has she walked? Well, we can answer that question easily, by just adding up 5 and 3. But the question is, how far away from home is she, is really the question concerning this. How long is this displacement? Well, in order to do that, we need to know the direction. We need to know the length. And in order to do that, we need to find the length of a third side of a triangle. Well, as you can see, this triangle is not a right triangle, so we can't use trigonometry, but we can use something involved with trigonometry. And if you thought law of sines, law of cosines, you're absolutely correct. Because we have two sides and the angle in between the two sides, we can use law of cosines. And law of cosines looks like this, where this is my A, this is my B, so A squared plus B squared minus 2 times A times B times cosine of the angle in between. When we do that, we get an answer, but that answer is only for x squared, not for x, and so we take the square root, and we have an answer to the second question. We know she walked 8 miles in general, but she's actually 7.4321 431 miles away. I forgot the miles. Okay. And they said, what is her net displacement, which is how far has she actually moved, like the angle, like what direction. And so in order to do that, we need to figure out the angle theta that she has made. And the angle theta is the angle formed by the displacement vector as well as, displacement arrow as well as the horizontal axis. And so in order to do that, we use law of sines, which is the sine of this angle divided by 3 miles is equal to the sine of this angle divided by this length, which we found to be 7.431. And using our algebra, we get this for the sine of the angle. And using inverse trigonometry, we get this as our angle. So now we can say that the net displacement is actually made up of two things: the length, which is 7.431 miles, and with an angle of 16.588 degrees approximately. Okay. I just want to point out the order of addition does not affect the sum. Whether we added 3 and 5 a different direction, we still would have gotten the exact same displacement vector, and we still would have gotten the exact same angle, and that's because of geometry properties of parallelograms. So same length and then same angle in this case. All right, let's move on. We're going to talk about the concept of vectors and how they are related to displacement. Vectors are another way to describe displacement. Remember, displacement measured or included the measurement of separation and direction. Vectors include the measurement of magnitude and direction. And here's the notation for a vector, the actual geometric shape. And here's the notation for the length of the vector, which is considered called the magnitude. And we can also use an angle to represent the direction if it's not a north, south, east, west direction. And here are the different areas of study where vectors are used. So it's not just a math or science concept, even though all areas of math and science can use vectors. All right, so moving on, let's talk about this situation. How do I add two vectors? Again, vectors are geometric shapes, and what I talked about earlier was if I want to find the sum of two vectors, u and v, I place the head of the second vector at the tail of the first vector, and then I draw a line or another arrow that starts at the head of the first vector and ends at the tail of the second vector after I've placed it that particular way. And so this vector looks like this, the w vector. And I can find the length and the direction using law of sines or law of cosines if the triangle formed is not a right triangle. Let's look at an example of this. Here they want us to find the magnitude of this vector mj. And then they want to find the direction of that. So it's something similar to what we did before. We have to find the length, and then we have to find the angle. This is a little bit tricky because this is what the drawing they gave us, and this is not necessarily how you would draw a vector, the addition of two vectors, because you kind of have to put the head of the second vector at the tail or vice versa. But what we saw previously is order doesn't matter. So I'm going to draw this to represent my FM. Okay, and I'm trying to figure out what this angle is. And I kind of already know what that angle is because that angle, if this is a parallelogram, because if these two sides are parallel and this third side is parallel, I can't draw, but just assume this, then these two angles are supplementary. So this would have to be 110 degrees. Why is that important? Is because I'm trying to find the resulting vector, and the resulting vector, I can't draw a straight line, but it looks like here. And so I know that this is 8 and that this is 3, and this angle here is 110 degrees. So I can still use the law of cosines to come up with the magnitude squared, and then use square root to figure out the magnitude, which is 9.456. Using law of sines, I can also use the fact that now that I know what this length is, which is 9.456, I can use, and I know that if this angle is 110, I can also determine another angle. Determining this angle will determine the direction, and so I can use law of sines as well. And I end up with this as my sine theta, and then I end up with this as my angle. So now I have the angle and I also have the displacement as well. So that's enough for me to figure out that information. Okay, how do we subtract vectors? Well, subtracting vectors is a little bit the same as adding a negative of the vector. So if I say W is equal to the subtraction or the difference of U and V, if I add V to both sides, I get that W plus V is equal to U. So in other words, even though we're not talking about numbers but vectors, what vector do I add to V to get to U? That would be my answer for my subtraction vector. Okay, so here we have U and we have V, and the question is, what vector do I add to V to be able to get U? Okay, and this is the vector that I add to V. Remember, head to tail, and this is the vector, and that's what W represents. Okay, all right. What about multiplying vectors? Well, it's very easy to multiply vectors. If when you're multiplying by just a number, you're only affecting the length or the magnitude of the vector, not the actual displacement. So the displacement will be the same. And so no matter which value, if the scalar is a positive number, the displacement will be the same, exact same. If the scalar is a negative number, like in this case, the displacement will be in the opposite direction. And what if the scalar is 0? Well, then you have 0 displacement, which is 0 and 0 magnitude. So here's a little chart to help you remember the results of scalar multiplication, where k is any number. And in this case, this tells you what happens when k is positive, when k is negative, and when k is equal to 0. All right. Scalar multiplication and vector addition is very similar to adding and subtracting and multiplying numbers. And so it looks very much like a numeric relationship, but just remember that we're talking about vectors here. So this should help. You should understand this from earlier math classes, and now that we're applying it to vectors, it means the exact same thing. So these are properties that hold for vectors, even though you're used to seeing them with numbers. Okay, we're almost finished. 12.2 talks about the components of a vector, and this is a little bit different. A unit vector is a vector of length 1. Okay, so let's say I have an x-axis points east and the y-axis points north, and a person walks 3 miles east and 4 miles north. How can I express her displacement, not just in terms of the vector, one vector, but in terms of the unit vectors I and j? Well, if you recall, the displacement is 3 miles east and 4 miles north, so that must mean that the east vector is 3i, since the unit vector has a length 1, and the north vector is 4i. So therefore, this is how we would represent the displacement of the way that the person walked, only in terms of vectors I and j. It's just a different way to express a displacement instead of just using one vector. Okay. Now you may hear the phrase resolving a vector in the plane into components. That's basically mean breaking down a vector into smaller components like unit vectors, as we saw up here in this example. So let's see right here. I have this vector v. What if I want to resolve it into components, i.e. break it into smaller components? I'm going to use the unit vector, and if you recall, a slanted side length is basically the hypotenuse of a right triangle. And in this case, my horizontal side is my x, which is also my unit vector vi, since it's pointing east. Let me V1, and then the vertical vector is V2 since it's pointing north. So the question is based off the information I have for vector V, what information do I have about V1 and V2, which are scalars of the unit vectors as well. So it's very simple. If I know what V is, I can determine V1 and V2 because of the magnitude. This is the right side of a right triangle, so this length can be found as the length of the hypotenuse times the cosine of the angle formed, and this can be found by the length of the hypotenuse times the sine of the angle. Okay, and so this is how we end up with our values for our V1 and our V2. Okay, very simple. We'll do more in the GEA. So in our particular example, suppose we had x-axis pointing east and y-axis pointing north. How could we resolve the displacement vector into these component parallel vectors? Remember, it was pointing east 3 and 5, so that's how we would do that. But we don't have time to do this, so let's move on. Displacement vectors. Okay, some of you may say that seems redundant, but it really doesn't because here we have displacement between P and Q can be represented by a vector, and P is a point and Q is a point. And so the question is, what are the components of the vector PQ? It's not -3, 1, and 2, 4 because those are points of the vector, but they don't tell you anything about the displacement vector. And so similar to the previous one before, we use this right triangle. We form a right triangle, and what we know is that the length of this can also be found without using cosine, just by taking the difference between the x values. So -3 and 2, the distance is 5, and the distance between the y values will tell you the length of this, which is between 4 and 1, which is 3. And so now we have something that looks like this, where I is universally understood to be the unit vector in the east direction, east-west direction, and J is understood to be the unit vector in the north direction and can be used for now north-south direction. Okay, I think that's it. Oh, we have one more thing. That's vectors in 2 dimensions. We can have vectors in 3 dimensions, which was what we live in. And in case of, instead of just having a vector I and J, we have unit vectors I, J, and K, or X and Y and Z. As well. So you can have as many components as you want based off the number of dimensions of the vector. All right, I know that was long, but we covered 2 sections, so that's it. Thanks.